without any further delay, João, I'm gonna. Can you please share your screen? So our first presentation is a summary of the great work that João has been doing under his PhD on mining engineering. Well, I'm sure that he will explain. He will do an overview and detail some of the methods that they developed. And João, the floor is yours. Please go ahead and start sharing your.
Can you see my screen already?
Yeah, but you need to put it in PowerPoint slideshow. All right.
Okay, so welcome. So good morning. My name is João, and I'm a mining engineer. Today I will be presenting some of the research I developed during the last years. The following presentation will briefly resume that which forms the core of my PhD thesis conducted here at IST. Okay. I was fortunate to be invited to work as a researcher in the real-time mining project, a consortium between European leading industry and academic expertise in the mining technology that sought to bring the mine industry into the 21st century. I developed my work under the supervision of Professor Amilcar Soares and in close cooperation with the Neves Corps of Mine staff at Somincor, who not only supplied us with the data and access to the mine, but also, and more importantly, because they trusted to test and implement our solutions in a real complex underground mining scenario, providing invaluable and constructive feedback. So the real-time mining framework proposes the transformation of the traditional linear mine value chain, which goes from exploration to modeling, mine planning, production, processing, and sales in a linear way. And between these elements, there is usually a time and information gap between operational elements of the chain that range from weeks to years. So the proposition was to change that into a closed loop from an intermittent to a continuous mindset, shortening the time and information gap between the various elements of the mine chain. With a fundamental innovation in some key elements, for instance, we proposed a real-time update of the resource models and using online IIoT-based sensors. One of the great opportunities the RTM, or the real-time mining framework, brings is the chance to work over the meta interfaces of the mine value chain elements in an interconnected and comprehensive way. And this is important, for instance, because the mining reserves, or the reserves estimation, it lives at the interface of the resource model with economic constraints and technological constraints, so it lives here. Likewise, the data accessibility and the data availability also live at the interfaces between mine value elements, and they will in turn influence the resource model. So to account for these meta interfaces, the real-time model framework proposed an extra element in the mine value chain, the central hub, where information flows in and out of, and where the KPIs are permanently measured and compared. So we have scheduled versus production, prediction versus measurement, model versus measured reality, allowing for a dynamic response and course adjustment in real time. By centralizing the automatic KPI reporting and analysis system, the RTM framework enables the creation of a real-time reporting tools that can be used for information transparency and accountability, creating direct interfaces with mine project stakeholders such as governments, environmental agencies, local populations, and so on and so forth until the shareholders. So now the concept of real-time mining framework brings an overall shift to all levels of traditional mining operations. However, the scope of our intervention lay restricted in only these meta interfaces here. So the first one, we developed a way to integrate the uncertainty data from the online sensors into the resource model. Then we developed a new algorithm for real-time update probability resource models. And then we provide a way to access the uncertainty characterization at the mining reserves, and finally a new estimation to solve some particular problem with the underground mining reserves models. So the real-time online information collection is built on a different mindset from traditional data collection. So while traditional geologic data collections involves sparse and parsimonious sample retrieving and lab analysis, yielding certain but expensive data, real-time IIoT-based data is comparatively much cheaper, can be collected and processed in enormous quantities, but can be highly uncertain. So the innovation lies on coming from here into here. Our approach was to build a history-based sensor uncertainty characterization model, which allowed us, through the use of conditional stochastic simulation, and more specifically direct sequential simulation with local distributions, to integrate the uncertainty of the data into an operating resource model. The methodology was successfully demonstrated with excellent results using data from a real ore deposit at the Neves mine, the Zambojal ore body, and the work has been presented in several conferences and published in Mathematical Geoscience. As you can see, the resulting models are fairly similar. The main difference, however, is that this one is much, much cheaper to produce. So the next challenge was to take the real-time new information and translate it into a real-time modeling update. The idea is to go from the collected data into a simulation ensemble model whose information is re-encoded into a probability resource model which can be updated. Our approach was to use a custom developed probabilistic cloud update algorithm derived from the inferred covariance model that uses, I'm sorry, I need to take this out of the way, that uses a symmetric node resimulation and weighted quantile interpolation mixture models to update the probabilistic resource model in real time, as you could see, if I can take this away. The pointer, yes, as you can see happening here with this reference case. So then we integrated the uncertainty characterization model update into a mining reserves and production schedule. Okay, with our real-time fast data acquisition and real-time update resource model, we want to access the uncertainty characterization at the mining reserves level. To do that means preserving the uncertainty characterization through production scheduling, the transport, ore pass, stockpile blending, all of that, which requires the access of uncertainty at different support levels. I'm not sure why this is not. Okay, which requires a way to access the uncertainty at different support levels and material mixtures. Our approach to makes use of the probability resource model, recurrent feature in this presentation, from which a non-parametric representation of the distribution of each production stop can be assessed independently of the final volume it may have. Then using quantile interpolation model and Monte Carlo simulation, the uncertainty can not only be used to assess the production schedule level, but also used to condition the algorithm, the optimization algorithm, to facilitate different exploitation strategies, such as the internal production blending or the maximum selectivity strategy, which has the added bonus of providing us an uncertainty minimization into the production schedule. Okay, this work was also presented in several conferences and recently published in Mathematical Geosciences. Okay, so the last one is aimed at solving a particular operationalization problem at the underground mine operations. So a brief contextualization: while the surface mining and open mining production schedule optimization have been subject to intensive study, and we have algorithms to optimize them, such as the Lagrassmann based operational research algorithms, and even optimal open pit production schedule under geological uncertainty using simultaneous stochastic optimization, which are both simplex based with graph metaheuristic algorithms. The same cannot be said about the underground production schedule optimization problem. In fact, the underground production schedule problem has been described as a combinatorial nightmare and has been demonstrated to be NP-hard. There is as yet no formal nor any putative optimal solution to the algorithm.
João? Oops. Something.
Sorry?
João, sorry, you were froze, I think, at least on this side.
Okay, what about now?
Now it's okay. Go on, go on.
Okay, so essentially what I was saying is that while we have a solution for the underground mine problem, we don't have a solution for the surface and open pit production schedule. We don't have a solution for the underground mine schedule optimization problem. This is done manually, and it takes many hours for experts to develop a single plan. The underground production schedule optimization problem is therefore a human resource critical part of the mining operation, and it represents a choke point in the implementation of real-time mining framework on complex underground mining operations. Today, complexity and scheduling makes it so that mine planners can only work with a single image resource model, which for the most part means using a Krieg model. So a simplified workflow from reality into mineable reserves estimation can be described in this way. We have reality from which we sample, then through statistical and spatial continuity analysis, we produce a variogram model, and then the data and the variogram model run through Kriging, a Kriging routine, which gives us a Kriging error variance and our estimation, the Krieg mean. Then we take into consideration, okay, so the Krieg mean is a single estimate, but it's also the best linear and bias estimation. So that is important later on. Then we take economical and technological constraints and we fuse them all together into a mine planning routine that provides us the minerable reserves model. So the conceptual approach with this to do the same with stochastic simulation gives us a neat type, which and a local variance, and the E-type is equivalent to the Kriging, so there is not much value on using the E-type. However, there are no efficient workflows to work with the multiple images of the ensemble. Currently, the process is too complex and too lengthy to automate or replicate n times at scale by hand. We propose an interim solution while no such algorithm or workflow is available to do this using the ensemble directly. Again, we make use of a resource model, then our data is crossed against the probability resource model into a collapse function. Here, I will not go into detail as time is short already, but I can say we took a page from quantum mechanics textbook and assumed that the reality is but a collapse of the state functions of a range of possibilities. This is concurrent with a geostatistical formalism from where we assume that the state function is represented by the local distribution as we access that from the probability resource model here. The outcome is a new variable, the probability of collapse of reality. And then we use the same workflow as before to produce an ensemble of models of that same probability throughout the whole model. The E-type or the mean of that ensemble gives us the probability or will give us the uncertainty. Then we reverse query the probability resource model, and we get to our new estimation, which we dub the P-type. Then we can use the exact same routines that mine planners are used to with Krieg models to produce the mineable reserves. So the question is this this is a single estimation like Krieg, but it's updatable and it provides an uncertainty characterization. Actually, it gives us the probability of being correct. So is it any good? To evaluate that, we used a reference reality. We then sampled that reality with a stratified sampling approach, and we used the Krieging workflow and the stochastic simulation workflow to produce the Krieg and E-type, which are equivalent and equal here. We also compute the mean absolute deviation, another estimator used by the industry sometimes, and we compared it with our own new estimation. As you can see, our estimation can reproduce the low-grade areas as well as the high-grade patterns, very similar to the reality, even though we have sparse sampling, and it's much better than either one of the other estimators. Here we can see the error maps. As you can see, we have much wider in our estimator, which means lower errors. In fact, when we compare the error profile to the histograms of the error profile, we find out that our estimation is actually more unbiased and centralized than the best linear unbiased estimation. Thank you for your time, and I am now open to any questions if you have them. Thank you.